number theory seminar. I have to resist the temptation to say good afternoon because it might not be afternoon where you're listening in from or tuning in from. But I hope it's a nice day wherever you are, nice time of day. Anyway, our speaker today is Steve Kudla from University of Toronto, and he's going to speak on the subring of special cycles. Steve.
Okay, well, thanks very much for the invitation to come speak in this seminar. All of us are learning, I suppose, how to do these online non-chalk talks. So we'll have to see how it goes. As you'll see, I declined to spend the time making a formal Beamer presentation out of this, which would take infinitely longer, at least for me. So instead, you're going to have to put up with what you see here, which is a sort of a set of notes, which I gave a lecture from once upon a time. So basically what I want to look at is these orthogonal Shimura varieties. So the point is that as we often have experienced in the past, when you look at orthogonal groups of signature M2, I'm going to go through all this detail in a moment. It's a sort of a bounded domain, a symmetric space attached to this thing, and it makes these nice orthogonal Shimura varieties, which include the modular curves, Hilbert modular surfaces, Siegel modular varieties, et cetera, as special cases. But it's traditional to kind of more or less work over Q, where indeed those three things I mentioned are special cases. And of course, you can do something quite a bit more general, and that is to say you can work over a totally real field of degree D with a quadratic space where the signature has got a certain number of M2s and a certain number of M plus 2 zeros, where the D plus is the number of non-compact places and D minus D plus is the remainder. And so you can work on Shimura varieties built out of this kind of situation, and the geometry actually gets quite a bit more complicated just because of the fact that now you have many factors and so on and so forth. So the purpose of this talk is to discuss these special cycles, which John Millson and I studied many years ago, the last century, but study them in this context. And the point now is that you'll see that there's some new phenomena which arise. And one of the things I wanted to try to look at in this particular case is to not worry about the Chow groups, which is maybe what one's ultimate goal might be, special cycles in the Chow group. But what I wanted to look at is just the special cycles, the cohomology classes carried by these special cycles in this situation. And it turns out that you can say something. So I was interested in, or found out that I could say something about the ring structure. So it turns out that these cycles span a subring of the cohomology under cup product. And so the goal is to try to understand something about the structure of that subring, and along the way to try to get some comparison results. You see there's quite a lot of data that you can vary here. In particular, you can vary this quadratic space or the signature, or most importantly, this set of places sigma V plus. So sigma is the set of Archimedean places of F. Sigma V plus is the set of places where the signature is M2. So I think I've introduced already in talking a bit of the notation. So D is the degree of my totally real field. I have my quadratic space with this signature. So the dimension is M plus 2 over F. I'm going to let G be the restriction of scalars of the G spin group. We're going to make a Shimura variety out of this. And then the symmetric space in this situation will be gotten as follows. So for each Archimedean completion, V sigma is V tensor over F sigma R. So sigma is in a real embedding of F. D sigma is the negative two planes oriented, that's what the O means, inside of V sigma, that's D sigma. And there's a factor like this. So this is a Hermitian domain of dimension M. And there's a factor like that for each place in this set of places, sigma, in other words, for each of these places. So you take the product of those, that's our symmetric space. It has dimension M times D plus. And so D plus here is, this D plus, not that D plus, is one component. This D has two components, as we'll see that will play some role later. In any case, then you take a compact open subgroup of the finite adels and you make the double coset space, which gives you the complex points of the Shimura variety. And in this case, the Shimura variety, I'm going to really be studying this as a complex manifold. And so I don't really care very much about the field of definition, but you can work it out as some sort of a reflex field depending on this set sigma plus here. I don't care what it is at the moment. Of course, they have models over number fields. In any case, if you notice that this variety here is a Shimura variety as opposed to a connected Shimura variety, the point is that if you write the finite adels in this way, so remember I've restricted scalars, so I can talk about GQ. GQ plus is the things with totally positive spinor norm. If I write the double coset space like this is some finite collection of GJs giving you double coset representatives, then in fact this Shimura variety looks like a finite union over the same set of J's of gamma J acting on D, where gamma J is this GQ plus intersect this conjugate of K. And there probably should have been a plus here because I want this to be connected, and that's why I'm taking GQ plus. Sorry, there's a typo already. Anyway, the point is that these things are not connected, and this will play some sort of a spoiler role as we go on, that the results are not as strong as they could be if it were. So anyway, I'm only going to be interested in the case of compact Shimura varieties. I'm not going to worry about what goes on in the boundary. And so I'm going to assume two things. First of all, I'm going to assume that the space V is anisotropic. So there are no null vectors, non-zero vectors, which are with zero inner product. And I'm going to assume that K is neat. So those two things together mean that this SK is a smooth projective variety over the complex numbers. Neat makes sure that that these are manifolds, these quotients, and the projectivity is becoming from the fact there are no cusps here. So this is a nice smooth projective variety for each K. And so we're interested in its cohomology. So S bullet K, so this is the cohomology, of the Shimura variety. And then at the top degree, there's a degree map. Now, I've already warned you that this variety is not connected, and therefore we have to understand the degree the correct way, and that is to say it's the sum of the degrees over the components. So this is, again, something I'll mention later, but this is what degree means. It's the sum over the different components. But moreover, that's a little off. That's what I would call degree natural, or the naive degree, namely just take the sum of the degrees over the different top degree components of the variety. But then I want to normalize by a volume. Z is the center of G spin. So I want to normalize by this volume. And this has the property that it means that the degree map will be well defined on the direct limit. So of course, if I have K prime contained in K, a subgroup, compact open, I get a projection from SK prime to SK, and I map the other direction on cohomology, and I can pass to the direct limit over all the Ks and get a cohomology group here, which is of course topological, blah, 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 and K, the GAF acts on this thing. The K invariants are exactly recovering the SK and so on at a finite level. But the important point about this normalization of degree is that on the top degree in here, this degree map is well defined. You know, this volume thing exactly makes it a well-defined map on the top degree here. Okay, so that's why the normalization. Okay, so this is the group this is the cohomology I'm interested in. But of course, all these things are graded rings under cup products, and therefore the limit is a graded ring under cup product. And moreover, there's an inner product, which I get by simply taking the cup product of two elements and applying the degree map. Now, the degree map is taken to be 0 if you're not in the top degree. So this means that classes which are not in complementary degrees, inner product to 0. So that's the way this inner product works, okay? And we're using in this inner product this normalized degree. So it passes to an inner product on this graded ring in the limit. Okay, now just to say a word more about components, as I said, this will come up later, mostly just in a comment. It's standard thing, this group, I didn't mention, of course, that I want V plus to be greater than 0. I want to have a Shimura variety. And in any case, that means that I have a strong approximation theorem for the spin group, and which is simply connected. And that means that pi 0 of this guy is standardly isomorphic to the this quotient of sort of an ideal class group of F. Okay, so this is pi 0 at level K, where you take the spinor norm image of K, and that gives you a compact open subgroup here. So this is the pi 0 of K. Of course, when I pass the limit, this group here simply gets smaller and smaller. And this is the totally positive elements, this thing I'm modding out by here. In any case, that means that H0, which is the dual of pi 0, and I'm passing to the limit, is just the smooth complex valued functions, I'm taking always complex coefficients. Again, you probably want to put in Tate twists and rational things, et cetera, but I'm not going to be, I'm just doing very crude things here. In any case, the H upper zero is just the smooth functions on this quotient space. Okay, so that tells you one of these cohomology groups that we're interested in, but in particular in there, there's the constant function, which I'm going to denote by 1. And also, if you have any character of this group, so this is basically a Hecke character, but it's trivial at on the connected components at infinity, as you can see from this, since it factors through this. For any Hecke character, you also get a class in H upper 0. So there are quite a few classes in H upper 0, and these are the ones which I can't say much about. I'll explain why a little bit later. One other thing that will play a big role in what I'm going to do here is the tautological bundles. So you see, d sigma can be also realized inside of the projective space of the complexification of v sigma. So it's exactly the isotropic lines such that WW in the complexification, such that WW bar is negative. And so this is a standard model of this thing. This exhibits it, by the way, as an open subset of a quadric. Here's a quadric in this complex projective space, and here's an open subset. So this exhibits the complex structure on this bounded domain. And on this guy here, I have O of -1, the tautological bundle, and I can pull it back or restrict it to d sigma. But also under the projection from d to the factor d sigma, I can pull it back again. And so I get a line bundle on d. And these line bundles all descend to the Shimura variety. And you can consider the following class, which is important in this discussion. Namely, you take the first Chern class of these guys, and then you take, which all are in H2, these first Chern classes. But you see there are d plus of them coming from the different factors. And so I take their product and I get a class, which I'm calling C sub S, in H2d plus of S. So there's this natural tautological Chern class floating around. And by the way, I've taken the dual here. And I guess the S here just indicates where I'm viewing this, and later on there'll be gammas when I do the same thing on some connected component. So this is a class in H2, and again, these descend independent of K, and so it gives me a class in the limit. Okay, so now let's talk about the special cycles. Now, of course, the point is that these kind of orthogonal Shimura varieties have lots of algebraic cycles coming from sub-Shimura varieties of the same type, and the weighted ones are going to be nice in the limit. So let me just describe those briefly. These are from deep in the last century. So I have my quadratic space over F, and let's suppose I have a totally positive F subspace of that. Then for each sigma, I can consider, since this guy is totally positive, I can look at the negative Q planes which lie in which are orthogonal to W. Okay, in the sigma factor in V sigma. And so this thing now will be sitting inside of D sigma. It's a cycle, and depending on the dimension, the codimension will be the dimension of W inside of one factor, and then in all factors it'll be that dimension W times D plus. So if W is simply a positive line, rational line, then I get a cycle of codimension 1, a divisor in each factor, but therefore in the whole thing I get a cycle of codimension D plus. So it's interesting here, this is one of the places where the phenomena is a little different, because what happens is that if you had worked over Q, then, for example, a positive vector would give you a divisor, and then everything else is giving you divisors on divisors. But here the codimensions go in multiples of D plus. And this makes the geometry much more complicated, in fact. Now, I mentioned at the beginning there were 2 papers that I posted on the archives about this, and the first one is about the Chow group classes of these cycles, and there you really have to work hard to deal with this D plus. I mean, you really have to look in Fulton's book and worry about how that works. Anyway, if we let pi gamma, so I have some discrete group, gamma acting on D plus, I make pi gamma be this quotient, I can define a cycle attached to this totally positive subspace is just the image of this dw plus, which is the product of these things, in that quotient. Okay. So ZW sub gamma is by definition the image of this DW. Okay, so it's a cycle of codimension n d plus, where n, I should have said here, n is RW. Sorry about n. N will later be n. Okay, so now to generalize this just a little bit, if I take an n tuple of vectors and I let W of x be their span, I'm going to define Zx sub gamma. Now this is going to be a cohomology class. The bracket I'm already passing from cycles to cohomology classes. What I do is I take the span of, well, if these guys span a totally positive subspace, I use that totally positive subspace by the construction mentioned up above, and I get a class in degree, well, the class will be in degree R2 x d plus, okay? So it'll be, the class will be in a dimension determined by the dimension of the span, and I want it to be in codimension in the dimension 2n d plus. And so I'd correct by cupping with this tautological bundle to correct if the span isn't everything. So you see, if the n tuple are spanning an n plane, so if they're linearly independent, this factor is gone and I just get the cycle as by the previous construction, and otherwise I jack it up by a power of this class to get a class in the correct degree, correct being the index n. Okay, so the class is in H2n d plus, and it has Hodge type n d plus n d plus. I should notice, for example, that if you took simply x to be 0, which is certainly allowed here, but it's an n tuple of zeros, then of course the positive definite business will be, this will be essentially just 1 by definition, and then you just get the nth power of the this tautological bundle. Okay, weighted by, okay, so now let's go to the weighted cycles. So this is the totally geodesic cycles. Now to make weighted cycles, you're going to average over different frames here. So what you do is you fix an n to symmetric n by n matrix, which is positive semi-definite, and you fix a function on the finite adels, n copies, and you sum as follows. So remember, there's a decomposition of your Shimura variety into connected pieces like this. This should have been a plus here. And on each piece, I'm going to define a cycle as we did before, namely it's the Zx gamma j inside of this piece. And as I vary the j, I get Zx gamma j's in each of the components. And then I'm going to weight them by this translate of the Schwartz function. And the important point, of course, is that, first of all, this is like requiring that my components lie in a lattice or in various different lattices, depending on which component. And so this, if I sum here mod gamma j, the x's of this property, I get a finite sum. So this is a finite cycle in the Shimura variety SK. It's a weighted cycle. Okay. So for example, if you looked at the x is 0, you would just get this nth power of the tautological class times the weight function evaluated at 0. Okay, for example. Now, why would you want to do this? The important point, and this comes from my old Duke paper from in the last century, when you look at a covering map like this, K prime containing K, and you have a pullback map, it turns out that if you pull back the cycle, which is defined here, ZT phi K, it pulls back to ZT phi K prime. In other words, the data T phi is invariant. So these have beautiful properties under pullback. And so you can simply erase the K and define a class ZT phi in the limit. So this defines an element in the direct limit, okay? So we get classes ZT phi in the cohomology sort of at overall levels. That's the main reason for passing to these guys. Okay, so now these cycles, these weighted cycles have many other nice properties. For example, one very nice property is the fact that when I look at their cup product, now of course I'm now working in this graded ring here as I vary the index. And so if I have two cycles with a TI, I equals 1, 2, oops, sorry. Uh-oh, okay, better. If I have two cycles, ZT1 phi1, ZT2 phi2, I can take their cup product. These are cohomology classes after all. And here's a formula. Namely, what you do is you look at, it's the sum over zt, phi1 tensor phi2. This is a Schwartz function of the correct degree, which is n1 plus n2. And you take T to be all n1 size n1 plus n2 symmetric matrices with the original T's as the blocks on the diagonal. And you get this multiplication formula. So this is a rather pretty formula, which is true in this situation. So these things have nice product formula for the structure of these guys. So what that means in particular is if I throw in this class in degree 0, which was just this constant class, I get a subring. These guys span a subring of the cohomology because the products are given here. And so we get a subring SC upper bullet of the cohomology, which I'm denoting like this. And notice I'm shifting the degree a little bit in the sense that everything is in multiples of 2D plus in cohomology. So I'm just sort of erasing the 2D plus. I'm using bullet instead for the grading. But anyway, you get a subring of special cycles. So this is the ring whose structure I'm interested in, and I'd like to try to say something about it. Now, the only way in which you can get some grip on the actual structure of this thing, at least as far as I can see at the moment, is via intersection numbers. And so basically, I will be able to say something about the actual intersection numbers of these, or cup products in these classes. And so what I want to do is I want to make a reduced version of this thing which might be a numerical equivalence. In other words, I want to only consider the classes that I can distinguish when I look at cup products with themselves. Now that's important. So what you can do is of course we have this pairing, which I defined earlier. So you take the cup product of two classes and followed by the degree. And I restrict this pairing to this subring of special cycles. And if you think about it, the cup product, the radical of this pairing, when restricted here, will be an ideal in this ring, okay? And so I could mod out by this radical and get what I call the reduced ring of special cycles. So here what I'm doing is I'm passing to basically numerical equivalence. So I'm doing special cycles modulo numerical equivalence. Now, numerical, of course, meaning only with intersections of other special cycles. So this is important. In any case, by definition, the cup product pairing induces a non-degenerate pairing on this reduced ring here. And I've erased the natural, and I'm now just writing nothing, since this is the main object of interest. Okay, so just to notice what happens. So first of all, I'm going to write little zt phi for the image of this big zt phi in this special cycle quotient ring here. And notice that, for example, the degree 0 part of the special cycles is by definition just the trivial class. And that will just be the same inside of this special cycle ring because there's nothing much to do to it. Now, if I go to the top degree, so this is degree m, notice I've shifted my grading. What is the radical going to be? Well, it's going to be the kernel of the degree map, because what I'm going to end up doing for something in this group here is I pair it with this class. These are complementary degrees, and pairing with this class and followed by degree is just taking degree. And so the radical is going to be kernel of taking degree. And so the special cycles reduced in top degree is just going to be all constant multiples of some class 1 check, which pairs to 1 with the original 1, okay? So the top degree has collapsed. And finally, in general, if I had a z, an m by m t and a phi, then little zt is just the degree. It should have been a k, well, the degree of this thing times that class. Okay, so you see how the collapsing is going here. Okay, now, so let me now mention the first result, which is a comparison result. So in any case, for every one of these v's, I've defined this ring of, reduced ring of special cycles. And so just as a reminder, quadratic spaces over the field F are indexed or characterized by their dimensions, their determinants, which determine the character, a quadratic character. This is what would be called the discriminant here. This is the Hilbert symbol, global Hilbert symbol, and this gives a quadratic character of the Gödel class group, and the signature. So, and finally the Hasse invariants, which are plus or minus 1 at each place. And the Hasse invariants are subject to the product formula equals 1. So the point is that if you fix the dimension and the chi, which is the same as fixing the determinant mod squares, if you fix the dimension and chi, then all you can vary are the signatures and the Hasse invariants. And one more note is that the Hasse invariant at infinity for one of these Archimedean places is going to be -1 for a signature M2 place and +1 for an M+2 0 place. So the choice between these two types of signatures will exactly change the Hasse invariant. So what that means is, suppose I fix a finite, the finite part of a quadratic space. In other words, I know what all the local Hasse invariants are, and I fix the dimension and chi and the local Hasse invariants at all non-Archimedean places. Then I can choose these signatures any way I want, subject simply to the product formula. In other words, the number of M2s, the parity of the number of M comma 2s is fixed, that's all. And you can vary as many as you like, so you can either take none of them or two of them, et cetera, and so on. So anyway, you see there are lots of quadratic spaces with a fixed finite part with a wide-ranging variety of signatures. Okay, so now here's a comparison result. Suppose I have two quadratic spaces with the same dimension and the same character, and such that their finite parts are isometric, are the same. So that's what the situation I just described. Of course, all that means is that d plus of v and d plus of v prime have the same parity. And I'm going to assume for the moment that they're both positive. Of course, I want Shimura varieties. Then what's true is that the reduced graded ring of special cycles, there's a map, and a linear map from one to the other. The map restricts to this. It says zv t phi to zv prime t phi prime, where notice this gives me a way of matching Schwartz functions on the two spaces. So you could identify the finite parts if you want and just say phi equals phi, but I'm keeping it in the notation. In any case, if you make this sort of formal map, there's no reason why this should extend to a linear map, but it does. And in fact, this gives an isometric isometry and a ring isomorphism of these rings. So this is a comparison isomorphism. And I find it a little surprising because notice that the dimension of the Shimura variety is not fixed. And the bullet here is the grading in this reduced grading, if you like, where I've shifted by d plus. And so you can get, for example, if d plus is, you could have one of them be 1, in which case you could have a single copy of d, d sigma, and the other one could be any odd number of places, and you'll get a much, much bigger variety. Of course, the codimension of the special cycle is also shifted. So anyway, I find this quite a surprising thing. And I don't know any geometric reason for it. And, it has a motivic kind of feeling. I don't know if there's a representation theoretic way of getting at it using some kind of a transfer of automorphic representations from one orthogonal group to the other, etc. I have no proof like that. Anyway, let's go on and explain how we get this. So the way you get this theorem, and I'm going to say something more about the cohomology ring reduced special cycles in a minute, is to go to these generating functions. Now you could make a formal generating function. You fix an n, which is the size of the t's, and it's also the space on which the Schwartz functions live. And you make this formal generating function zt phi, which is a cohomology class, times q to the t, and this is a formal q series, where q is q to the t, which really means e to the 2 pi I trace of t tau, where tau is a Hilbert-Siegel variable. Okay, so there's d copies of the Siegel space of genus n, and you take a Hilbert-Siegel variable, and this is the usual thing. Okay, phi here, of course, is a Schwartz function on here. So you make this formal q series. But what my old work with Millson shows is that this formal q series is actually the q expansion of the Hilbert-Siegel modular form of parallel weight m/2 plus 1. And so this is actually a modular form, a Hilbert-Siegel modular form, valued in cohomology. Now here, of course, phi is going to be fixed under some k. Phi will be fixed under some compact open subgroup k. And so you could really take this as living in the cohomology of the Shimura variety over at level k, if you prefer a finite dimensional coefficient space. In any case, the point is that the way this gets proved is by actually writing down a representative of this generating function valued in the de Rham complex of the Shimura variety, which is literally a theta function. And then that will allow us to compute cup products. So let me just describe very briefly how that works. The idea is, and if I put up some disastrous slides about a pre-talk about constructing theta functions, so that's supposed to be making this part of the talk easier. In any case, the idea is that if I look at any sigma, so I look at Vn sigma, so I'm looking at a non-compact place sigma, I can look at a Schwartz function on n copies of the real vector space sigma, but valued in nn forms on the symmetric space d sigma. So Millson and I constructed such a Schwartz function, which had this equivariance property with respect to the action of the orthogonal group, namely, if I pull back, so the orthogonal group is acting on differential forms by pullback. If I pull back this differential form, it's the same as acting on the argument. Anyway, I can take the tensor product of these guys over all these non-compact places. And here I take the Siegel-Gaussian at all compact places. And all of these functions are eigenfunctions of weight m over 2 plus 1 for the unitary group, both this and this. And therefore, when you make a theta function out of it, so here I'm taking that and augmenting it by this finite Adel guy, I make this theta function gotten by summing over the lattice, translate by the metaplectic group of this Schwartz function evaluated at x. So this is the theta distribution attached to this. This thing, and I didn't mention it on the last slide, but these differential forms here are closed differential forms on d sigma. And that means that when I make this theta function here, it's going to be a closed nd plus form on the Shimura variety. K, of course, is any compact open which fixes phi. And it's an automorphic form in G prime. And so now the modularity of the generating function comes by just taking the cohomology class of this generating series, and you get exactly the generating function. Here I'm taking some usual passage to classical language from Adelic language. Okay, so why is this going to be useful to us? Well, you see, we're interested in computing degrees of our special cycles. And so let me mention a couple facts that allow us to do that. You see here, the point is that I'm writing down an explicit de Rham cohomology representative of this generating series. Hence, in particular, a de Rham cohomology representative of each of these, all pasted together into a generating series. So the key crucial fact about these Schwartz forms is the fact that when I take their wedge product, one for n1 and one for n2, I get the one for n, which is n1 plus n2. And so what that means is if I make these generating functions that I just described, and I take their cup product, what I get is exactly the restriction to the diagonal of the generating function for the Siegel space of genus n. So there's this relation here between taking cup products of generating series and pulling back along this block diagonal the generating series in n for the n1 plus n2 generating series, okay? So this is on the de Rham cohomology, but of course what that means is when I go to compute, I'm going to use this formula. If I go to compute the pairing between two such classes, let's suppose that n1 plus n2 is equal to m. So these classes are in complementary degrees, or the cohomology is in complementary degrees. So the inner product is going to be the degree of their cup product. And that's going to be what you get by taking the wedge product of the de Rham classes and integrating over the Shimura variety. Of course, I'm normalizing, okay? But if you look at this formula here, it says, or this one, this basically says that if I take the cup product of those guys, and these will now add up to m here, this is a top degree form, so I can write it as a function times an invariant top degree form, and that's what I've done here. This is a function times an invariant top degree form. And so this integral here, in the next to last line, can be rewritten as an integral of a theta function against the Tamagawa measure over the orthogonal group. Okay, so this is the first step. In other words, because of the old work with Millson, I can actually write down these cup products as integrals of theta functions like this. But now the key point is that the Siegel-Weil formula describes such an integral of a theta function as a special value of an Eisenstein series. And so for this, how are we doing on time? Okay, pretty good. So I'm interested now in computing this thing here. And so the Siegel-Weil formula will give us this. So just as a review, I'm going to take G prime to be SPN, the symplectic group of size 2n. P prime is the Siegel parabolic, and it has in it, so these are the block upper triangular guys. I should have written them down here, but I didn't. Maybe I did in the pre-talk. And I look at the degenerate principal series attached to this thing here. Now here I'm going fast if you haven't seen this stuff, but the point is that this is a block parabolic with blocks with a 0 in the lower left n by n block. The MA is going to be something, A is in GLN, and the MA is going to have an A transpose A inverse on the diagonal blocks. B is a symmetric matrix, and the NB is a 1n, B, 1n. It's a upper triangular, block triangular guy. In any case, the degenerate principal series is what you get by inducing a character of the determinant of the GLN up to the adelic symplectic group. And the character I'm going to take will be the chi V, which we have, where the chi is chi V coming from our quadratic space. Okay, so of course, you can form from such an induced representation an Eisenstein series, which I discussed in the pre-talk. But anyway, there's a thing which I call the Wallace map, where if I take a Schwartz function here, on full adels here, not just the finite adels, there's a map to a degenerate principal series with an S naught gotten as follows. You take your Schwartz function, you move it by the symplectic group, and then you evaluate at 0. Okay? So this function evaluated at G prime is move the Schwartz function by G prime and then evaluate at 0. Okay. So if you look at how the induced representation, or the Weil representation is acting, so the group G prime, I should have said, is acting on this space by the Weil representation, the Schrodinger model. And if you look at the formulas for that, you discover that this function that defined this way is indeed in this principal series, where S naught is this magic number, half the dimension of V minus rho, where rho is this number half of n plus 1. Okay. Okay, so that's where you end up. And now what you do is you extend that, you extrapolate that to a section involving all S, making it constant on the maximal compact K. That's called a standard section. And then you can form an Eisenstein series for real part of S large, namely bigger than rho. And then what's known is that these series, which are now normalized in the style of Langlands, have a meromorphic analytic continuation and functional equation relating to S to minus S. And there, so you see the critical strip goes from rho to minus rho. And so Siegel-Weil formula in this formulation, remember I'm assuming that V is anisotropic, and this is something I proved with Wallace in 1988. The Eisenstein series, now you see, the point I'm evaluating, I want to evaluate at S naught. And notice that at S naught, this extra bit here, which somehow doesn't only come from phi, is gone. This interpolation is gone. So I'd like to evaluate at S naught. And what happens is that S naught can actually often fall, depending on the various dimensions here, inside of the critical strip. And so what's true is that, in fact, when V is anisotropic, there's no pole, and you take a section it's coming from the image of the Wallace map, the Eisenstein series is holomorphic at S naught. So we showed that there's no pole at this point for this data. Now, what's true is that if this point lies in the critical strip, there can be a pole for some data, but there's no pole for this data. And that means there is a well-defined value at S naught. And it turns out that this well-defined value is none other than the integral of the theta function built out of phi. So this is the Siegel-Weil formula. Now, I was a little careless here, sometimes a factor of 2, depending on where your S naught is, but I don't care. Good enough for now. Okay. And also I said earlier that when I was doing these geometric inner products or geometric integrals, I had Tamagawa numbers. And so in fact, it turns out in this case that this is also true. So you can just integrate over the Tamagawa measure on SO instead. So the Siegel formula therefore gives a formula. Remember, this is where we were trying to compute the inner product of two of these generating series, and we discovered it was a theta integral. And what we now see is that this theta integral, this inner product, is given by a special value of an Eisenstein series. So that gives us the following formula. I'm going to clean things up a little bit. You see, I want to evaluate at S naught, but there's this extra garbage that comes out in front here. So I'm just shortening the notation. And so now, here's what happens. That formula we had above specializes in this. The cup product is given by this special value at a half of the Eisenstein series. Notice that we are deep inside the critical strip here. Okay, so 0 is the center of the critical strip, and we're what you might call the Tate point if you were looking at motivic L functions here. Okay, but you see, remember there was this pullback relation, and namely the cup product here is the same as the degree where I've restricted this tau to be a block diagonal. So you get cup product is equal to a block diagonal pullback of the special value of this Eisenstein series. So this is a very pretty formula for the cup product. Now, you can view this as a geometric version of the Wallace inner product formula. And what it gives you is the following. You see, if I look at the Fourier expansion, so I have this formula, just repeating what's said in the slide above. Let's write out the Fourier expansions. What happens when I do Fourier expansions is that I have, just by definition, I'm expanding this as an automorphic form in tau 1, tau 2, so I get T1, T2 coefficients, Q tau 1, T1, Q tau 2, T2. So there's a Fourier expansion like this. It's a by Hilbert-Siegel modular form. And of course, this generating function also came to you in that way, where the coefficients are now the inner products of the corresponding classes, and these are equal. And so you get this formula, namely that the cup product, or the inner product of these two classes is none other than the Fourier coefficient of this Hilbert-Siegel-Eisenstein series. So this is one of actually the main results of this paper, and that is that it's saying that, in fact, the inner products of these special cycles, these weighted special cycles, are given by Fourier coefficients of Hilbert-Siegel-Eisenstein series. Pullbacks, rather, in this way. And notice that there's these very special Hilbert-Siegel-Eisenstein series coming by evaluating at this Tate point. So they're very low weight, as it were. So the genus here is M, and the weight is M over 2 plus 1. So these are very exotic Eisenstein series, in fact. And their coefficients give these inner products. But in fact, you can say more. And so what we're going to do is the following. Namely, let's suppose that you want to try a triple product. Namely, you consider 3 of these generating series and take their cup product followed by degree. Well, of course, you can view that as taking the cup product of 2 of them, the product of 2 of them in the cohomology ring, followed by inner degree with the 3rd one. So that would be looking like this. Here I take the inner product, or the cup product of 2 of them, followed by degree, map against the 3rd. But in any case, it's a triple thing, it's symmetric. And by the same argument, it's exactly the same argument, I get the same Eisenstein series, but with the triple data pulled back in a triple way, like this. And what I get, on the one hand, I get a triple modular form in 3 variables, which has a Fourier expansion in 3 variables as a Hilbert-Siegel tri-modular form. And on the other hand, the triple product, if you write it all out, will have a similar expansion where the expansion is going to be take the cohomology product of these 2 classes, which are not in complementary degree anymore, and cup product, or take the degree against any class in complementary degree. So here I'm assuming N1 plus N2 plus N3 is equal to M. And so these inner products here, namely take the product class inner product with this, are given by these coefficients. But you see, the inner product on this reduced ring of special cycles is non-degenerate. And so as soon as you know the inner product, the degree or the inner product of some class with all of these classes in complementary degrees, you know it because it's in the reduced ring. And therefore this inner product, this product class is determined by these numbers because now I'm running over all complementary cycles in the special cycle ring. And so what that means in particular, of course, we get this identity, but it means that this class, this product class, is completely determined by these coefficients. Okay? So the structure of this ring is completely determined by the triple pullbacks of Hilbert-Siegel-Eisenstein series, the Fourier expansion. So this is sort of interesting, and also notice, by the way, that although it feels like it's very much an Eisenstein world here, what's happening is when you do these pullbacks, there's lots of cuspidal components. So in other words, if you went, I mean, this is where the doubling method comes in, if you looked at degree, but here we have some sort of tripling version of doubling, and who knows what that is related to. But anyway, it shows that these things have a lot of arithmetic information. Okay, so this is how the comparison isomorphism comes about. Let me explain where that comes from. So now let's suppose that I have 2 quadratic spaces with the same dimension and the same chi. And then I have 2 Wallace maps, one for each of them, and with the same target, because the chi's are the same and the dimensions are the same. So I end up with the same target for the Wallace maps, okay? And so I make a definition, namely, I have Schwartz functions in these two different spaces are said to match if their image under the Wallace map coincides. So I call them matching if the image under Wallace map is the same in this induced representation. Now, of course, the point is that if I have matching Schwartz functions, then the associated Eisenstein series are just the same, because the Eisenstein series is formed by taking the image under the Wallace map, followed by extrapolating, followed by forming Eisenstein, blah, blah, blah. So as soon as you've got things coinciding in the Wallace map, the Eisenstein series are just the same. And what that means is that any information you squeeze out of one Eisenstein series for one quadratic space will then be the same as the information that you squeeze out of this Eisenstein series for the other quadratic space. You get all kinds of identities. I view this as kind of a poor man's relative trace formula. So in any case, the point is that the Archimedean part that we're choosing, remember we're using these Archimedean Schwartz functions, that the Gaussian and the M2 guys locally match. So this is something I didn't mention, but in fact, if I have two Schwartz functions, now remember, let's suppose I have that the two quadratic spaces are the same over the finite places. Well, then I certainly know how to match at all the finite places because I just take the same Schwartz function. But it turns out that all these Archimedean Schwartz functions that I'm choosing, regardless of how you choose the Archimedean places, match. And that means that these theta functions, as soon as you have matching at all finite places, you just get identities between all these things. So what that means is we get what I call automatic matching. Namely, if you have two spaces which are locally at the finite places the same, and with the congruence satisfied on the Archimedean signatures, then you get automatic matching. So the finite adels, as I just said, you just take the equality. And by the way, what's important here is that this matching has to be compatible with tensor products, which it automatically is in this case, and it is with respect to these Archimedean things that I'm choosing as well. So anyway, as a consequence, you get this theorem, which is what I had stated earlier as theorem A, or B rather, and that is that this gives me an isomorphism. Well, the critical point is to show that I get a linear map. And so here's the idea. What I'd like to do is I'd like to map the matching data classes to each other here. And so I have to show that any linear relation among these guys is also a linear relation among those guys. And that will show that there is a linear map on the generators, right? So suppose I have a linear relation among these classes in the source space in V. So this sum is 0. Well, what that means is that this inner product is 0 with any complementary degree class, right? That's what says that this is 0 if and only if this is true. But now what's true is that this inner product is the same as taking this linear combination of these guys, and that's the linear combination of these guys using the inner product formula in terms of Hilbert-Siegel-Eisenstein series that using the Fourier coefficients we had before. But of course, by this matching, these Eisenstein series are the same, so they have exactly the same Fourier coefficients. And so this combination equals this combination because these coefficients are just equal, because these are matching Eisenstein series. But of course, this, if you unravel this thing, is just the same as this corresponding linear combination of these classes, the target classes, inner product with an arbitrary guy here. And therefore, if this is 0, this is 0. And that means there is a well-defined linear map. And then the same argument here immediately gets you the fact that it's an isometry and a ring isomorphism, again, by comparing the product formulas, okay? Okay, so that's how the comparison isomorphism comes about. It's this comparison isomorphism. Now, there's one last little kicker here. I've got about 10 minutes left, if I'm okay about going a full hour. There's another question you could naturally ask here. In other words, in this whole business, I required in this comparison isomorphism that the parity of the D plus was the same for my two spaces. But now let's suppose that D plus of V is even. Well, I could, formally speaking, take D plus of V prime to be 0. Now, of course, there's no Shimura variety in that situation. But you could still ask, there certainly are attached to that totally positive definite quadratic space, there are Siegel-Eisenstein series and theta functions and so on and so forth. So you could ask, is there comparison isomorphism where one of these guys is allowed to collapse and you're allowed to take D plus equals 0? And the answer, amazingly enough, is yes. And so what you can do is the following, and this is some game I learned when I was in Oberwolfach in Happy Days in December a year ago. If you take, so I'm assuming now that the V plus is a totally positive definite space, and I'm imagining I'm going to compare it with a space where the D plus is even. So I take a totally positive definite space, and I'm just defining, there's no such thing as cohomology, there's no geometric Shimura variety, but I define this thing with a dot here to be the following thing. I take a truncated polynomial ring, so I take Z with a variable C, but C to the M plus 1 is equal to 0, okay? And I tensor it with the continuous functions on the Adel group modulo the rational points of this anisotropic, totally positive definite quadratic space where I'm looking at the finite Adels only. So this is some ring, and I can form this tensor product. So this is a truncated polynomial ring with these coefficients. And now I define a degree map on there, namely the degree of this CR is 0 if R is not M, and it's 1 if you're in the top degree. And then what I take is the function, there's a map Z, which sends a function here to this guy. I mean, after all, an element in this ring can be thought of as a function valued in this ring, or valued in C, right? I mean, that's what the element here is. So Z can be viewed as a function on here valued in this polynomial ring. And so its total degree is just, you take that function as a function in here, take its degree, which is going here, and then integrate that over this quotient, okay? Okay, that's total degree. So now I'm going to define weighted cycles. And now this should look somewhat familiar. Anyway, I can write down functions in this space depending on a Schwartz function and a t. I realize I'm running low on time. And I can define, notice that the t is n by n. And remember, if I had an n by n matrix, back in the day when we had geometry on our side, if you chose a t of size n by n, I wanted cohomology classes in degree n, or 2n d plus, right? The n determined the cohomology, even if t was 0. So I want the same to be happening here, and so I put in c to the n times this function which comes out of t, okay? So that's my the natural choice. These guys have a product formula. If you make this weird definition, you get the following product formula. This product is just the product in this ring, and this is what happens. As you can check, it looks familiar, which is a sign that you're on the right track. Of course, I can take the constant function 1 in this ring, and so I can define a special cycles cohomology ring by this formula. And once again, I can reduce it. I make an inner product using degrees, et cetera, et cetera. I can make a reduced ring out of that. And what happens is, well, here I'm discussing, I'm running short of time, but here I'm discussing what kind of collapsing takes place, and I won't go over that in detail. You can look in the slides later. But what happens is you end up with a reduced special cycles ring where you mod out by the radical of this pairing this artificial special cycles ring that I just constructed. But it's a very explicit ring. You see, it has only to do with these functions on this compact space. But these are rather, arithmetically speaking, contain a huge amount of information, all representation, lattice counting points, and so on. In any case, the point is that, well, in this reduced special cycle ring, there's going to be an inner product on the middle dimension, and it's going to be just the same as the usual inner product on this space. So this, in the middle dimension, if n is even, m is even, anyway. So now the amazing thing is you get this comparison isomorphism. Namely, if I have a quadratic space over F with D plus even, and I let V plus be the associated totally positive definite place, so I take D plus of V plus to be 0, then the finite Adels are taken to be the same, and I get an isometry of the finite part because those are the same. Then I get a linear map, as we were just discussing, which is a ring homomorphism and an isometry. So that means that this funny ring that I just constructed for you here out of functions on this positive definite guy, which is just a combinatorial artifact, is the special cycles cohomology ring of this Shimura variety. And the dimension of the Shimura variety can vary as you vary the D plus, as long as D plus is even. And so I think it's rather startling that you can write down, in some sense, all of these rings in this even case. Now, of course, when John Millson and I looked at these spaces before, and a lot of other people looked at these spaces. They always took D plus equal 1. And the reason was that you want to just compact OM to Shimura varieties. And so it was natural to look at the sort of Shimura curve analog instead of having multiple copies. So you see, this is a phenomena that only arises when D plus is even. And you can ask, what does this ring look like? I have no idea. I didn't do any calculations of examples. That's a question. Do these comparison isomorphisms, as I said, have some kind of motivic origin? Is there some motivic meaning for this guy? Or automorphic things? Is there a combinatorial model in the odd case? So if D plus is odd, is there sort of some standard model in that case? I don't know. And then finally, one last little comment, which I didn't write in the slides, and that is that I'm constantly having to reduce. And that's because, basically, if you look back carefully, basically I'm constantly having to reduce, at least in part because of the disconnectedness. If you look way back at the beginning, my Shimura varieties had many components, and there were these Hecke characters chi, which were characters of the component group. And so you can make chi-weighted cycles. And so what's needed here to extend this theory to the chi-weighted cycles is a chi-weighted Siegel formula. And this is something I'm working on. So that's all. Okay.
Very good. Thank you, Steve.
Okay.
Do we have questions? Somebody raising their hand? I don't think we're a very large group, so feel free to speak out if you want to ask something.
Well, let me just ask
Yeah.
quickly. Do you also have in mind an Arkelef comparison for different different quadratic spaces with the same parity?
Well, there should be something in the sense that if you believe the arithmetic Siegel-Weil formula, arithmetic Siegel-Weil is coming out of the central derivative of this incoherent Siegel-Eisenstein series. And so the matching of data at finite places will be the same game, right? And so, okay, when you put in the S and then look at central derivative, you should see again, under certain circumstances, you should be seeing the same Eisenstein series, right?
Mm-hmm.
And therefore you'll see the same Laurent expansion at 0, same constant term and so on. So yes, there should be such a thing. But I haven't done it, but I mean, it's the same technique in principle should go in that direction.
Any other comments? So Steve, this combinatorial way of looking at it by using the definite spaces, what more can you do with that? I mean, it looks like you've got a pretty neat tool there.
Yeah, I have no idea, to be honest. I mean, what's true here is that the difficulty is just that to do actual computations of examples, you would have to really work over a totally real field. So you could take, for example, a real quadratic field, and then what you would want to do is now remember, I'm always taking things to be anisotropic. So if you take real quadratic and you want D plus to be even, then you're very restricted, as over Q, right? Because you're going to hit Meyer's principle almost right away, right? So the dimension is very small. If you take a real cubic field, then you have lots of possibilities because you take any two Archimedean places. But of course, and then you could actually try to compute. In other words, you get lots of examples where you take a totally real cubic field, take the D plus to be the Archimedean places to be any two of the three places, then you get a compact, etc. Shimura variety, and then you could make the corresponding positive definite space, and you could try to do computations. But I have no idea how to compute these functions. Now, of course, the other thing that I didn't mention here is that you should be able to now remember, because all these spaces are being compared, they're literally the same at the finite places. And all these formulas have to do with the things at infinite level, but you could put in K invariants for a compact open, and the Ks will be the same because all the finite part is the same. So I think it's quite feasible to fix the finite part. In other words, to be on some finite dimensional thing. And so, for example, you could take K to be a stabilizer of a maximal lattice, and then you're only going to have class number indexes for components and so on, right? But again, you're going to be looking at the positive definite quadratic lattices over a totally real cubic field and lattice point counting issues. I have no idea what computationally how hard that is, right? And to be honest, I've never done any computations with these things. I mean, you can play around. Back here, I was discussing a little bit what collapsing takes place here. I guess that's in this previous slide here. So there was some discussion on what kind of collapsing takes place. Sorry, here in the reduction. But I haven't done anything non-trivial in terms of computations. It's an interesting question, right? Or can you even say anything with any of these formulas? Namely, if you make estimates on Hilbert-Siegel modular forms of these pullbacks, what can you say? If you allow Hecke eigen properties, in other words, on all this business, you could certainly have Hecke algebras acting at all the finite places, and you can look at the triple of restrictions is going to be triple of Hilbert-Siegel modular forms, right? And so you could then just take the eigen systems for each of the 3 components or 2 components, whatever you like, and so on. I've done none of that. So there's lots of possible games to be played here.
You remember there was an old paper of Gross where I think he was looking at unitary Shimura varieties, and then he looked at the definite versions and he got some combinatorial way of describing them.
Yeah, I'm not sure. Did he have a comparison then between the two?
I just don't remember, but then he used it, I think, to get a Wallace-Map type formula.
Yes, right. I mean, I think that was an early version of this Gann-Gross-Prasad business, if I remember right. Because it might have been, it might be there that you have a UN and a UN minus 1, where maybe the UN minus 1 is anisotropic or compact even. I'm not sure. I haven't looked back.
Any other comments or questions people have? No? So then let's thank Steve again for a wonderful talk.
Thank you.
You can't hear this, but we're all applauding. And are you going to post these slides?
Yeah, I think this thing I gave
Brian
already.
Okay,
So
excellent.
Excellent.
So I just want to remind everybody who's attending the seminar that the seminar is meant to be able to, it's meant to be accessible to people who are not particularly working in this area, especially students. So you might have noticed we always post a prep talk, which I encourage students especially to review before the talk. And then you can listen to the talk, and then when the speaker is able to do that, they'll be posting stuff, either notes from the talk or links to the literature or something. The idea is to really make this as accessible as possible. So thanks for coming, and I'm not sure who's speaking next week, but once I figure that out, I'll announce it. Okay, thanks.
Thanks for coming. See you. Good to see you all.